Hello, hello. Enthusiasm, I like it. All right. Let's go. That one does that one, that one does that. All right, cool. I'll let people get settled. All right, so we're gonna go over the tool changer and kind of new products from E3D. I'm gonna try and make this as much as possible not a rehash of what we did at Midwest, because I know a lot of you people saw that already. We're going into a lot more of the detail and kind of nitty gritty. Please, if you have any questions throughout, please just show up a hand, answer. More than happy to take questions throughout. I am well known for rambling on, which is why I think they've tactically put me at the end of the day. So hopefully we'll have a good amount of time. Cool. We'll start with kind of what we've been doing E3D-wise, so separate from the tool changer. Can't see much. Essentially, things that we've been doing on the E3D side is we've been really overhauling the way machining happens. We've got a lot of upgraded machinery, and along with that comes with upgraded capacity. A great deal of the work that we've been doing is actually for our partners who manufacture printers. They make up the majority of our business nowadays, and so a lot of our efforts have been put into scaling, which is difficult for all of you people doing startup. I'm struggling with being able to see what's going on. We've drastically improved our heaters. Heaters are a huge problem for everyone in the industry. Having a heater that maintains temperature over time, doesn't degrade, has a long mean time between failure, and has the ability to basically resistance tolerance has been a real big issue. So those are about 3-4 times better than they've ever been before. We are also introducing kind of new materials all the time for nozzles for various applications. I can't read my own slides, so I'm going to push on because this is the boring stuff. Super volcano. We were supposed to have one on the stand today, but all of our stand equipment got held up in customs. So Super Volcano is pretty much what you would expect. It is an elongated version of Volcano. It has about 3 times the throughput of Volcano, which in turn has about 3 times the output of V6. So it's about 9 times the volumetric flow rate of polymer compared to a standard E3D V6. So obviously this is designed for large machines, and we can just push a lot of plastic through it very, very, very quickly. In order to do this, we had to up the amount of power going into the heating system. So we are going for, I think it's about 80 watts on the heater cartridge. In order to do that safely, we had to make the block out of a special copper alloy that has an extremely high annealing and softening temperature. If we were simply to put the 80-watt heater cartridge into an aluminium block, as we normally do, then in case of a thermal runaway event, what would happen is that the block would get hot enough that the aluminium would melt, and melting aluminium sets fire to things. So that is a bad, bad idea. So we moved to what you can see there. It's kind of dark looking because it's been running at temperature. But in production, these will be nickel plated. So it's a nickel plated copper alloy with an 80-watt heater cartridge inside and big, long nozzle. So it fits on any standard E3D product. So that includes, your Titan Aero, normal V6. You could even do a 4 Super Volcano Kraken if you wanted to go down that route. So that is all possible. It just goes on your standard heat break. We've been talking about this a lot. It's been taking a while to kind of come to fruition, but we have a new nozzle material and coating. So we have we'll talk about our motivations here to begin with. So we have our very popular hardened steel nozzles. They're made of an A2 grade tool steel. Those are great and fantastic. However, they have two minor downsides. One is that the surface finish on them we coat in black oxide, which is, you'll often see black oxide coating on fasteners and things like that. It's a useful surface finish for preventing corrosion. However, it's slightly rough and has quite a high surface energy, which basically means that plastic likes to stick to it and accumulate on that surface. So we wanted to get rid of the black oxide coating, and we also wanted to be able to maintain hardness at higher temperatures. A2 tool steel begins to temper and lose some of its hardness when we go beyond the kind of 300 degree range. We start dropping down in the Rockwell C scale. I think that by default A2, or the way we temper our normal hardened steel nozzles, they're around 58 to 60 Rockwell C. The new alloy that we're using maintains its hardness above 60 Rockwell C, even up at temperatures where you're printing PEEK and the like. Then it's also an inherently stainless type of steel, so it doesn't need surface finish coating. However, we have come across a coating, it's called WS2. We'll be kind of talking about the details for it. It's not a total 100% panacea for getting rid of all plastic sticking to the nozzle. But it does greatly reduce the amount of buildup that you get, and so it's really useful. It has a couple of other side benefits as well that we didn't really expect. The first of which is when you're laying down your first layer, oftentimes, first layers like to peel off, especially if you're doing a track that kind of doubles back on itself. You'll often have that track start to peel up. Because we've reduced the stickiness of the nozzle, the plastic just likes to stay on the bed a lot nicer. So actually the reliability of your first layer increases, which was kind of unexpected for us, but pretty neat to see. The other is that the top surface layers of your print come out like really glossy, really nice. So we tried putting this coating on pretty much everything, including our brass nozzles, to see if it would be a good addition there. Basically, the surface finish is about as wear resistant as the material that you put it on. So if you put it on brass, it will kind of wear off fairly quickly within 100 hours of printing or so. It will come off with the flow of polymer. So it's about as hard and as tough as the nozzle that you put it on. So it kind of follows that we put it on our hardest, toughest nozzle. On there, it lasts thousands of hours, I would say, but it doesn't last for absolutely ever, particularly not on the very tip of the nozzle. On the cone and the places where it kind of really matters for buildup, I mean, the main criminal here is PETG. Like if you guys have printed PETG, you'll know you get that like clump of goop on the nozzle. The goop falls off into your print. It leaves like a horrible chunk. This gets rid of that. It stops that happening, which was kind of our objective, and also for like metal-filled filaments as well. Your bronze fill, all the kind of woody stuff that builds up. It stops that from happening, and so increases the reliability and quality of those prints, which is nice. Yeah, this is an interesting one. There's been a bunch of tests and data that I've been wanting to gather for ages and just never really having the time to do so. So we built this rig, and it's so freaking cool. There's going to be a huge blog post coming out. I won't go into all of the details of the findings, but it's cool enough that I wanted to show it off here. So we can put an extruder and a hot end into this thing. We have a high precision encoder at the top that watches the motion of the filament, and we also have a strain gauge that is observing the amount of force required to extrude at any given time. And so we can extrude at different speeds, we can do retractions, we can see how different retractions result in different forces. We can also quantitatively analyze things like back pressure in nozzles, how changing internal nozzle geometry affects the way that polymer flows through the nozzle, and analyze, you can really get into the woods of things. And so our motivation for doing this is for a product that's coming out later, that we're not quite talking about yet, so we'll leave that one covered up. But really, as I've kind of written up there, as we kind of get close to the absolute limits, like at the moment, 3D printing, extrusion, we've got it reliable, it works great, but now we've got to like really optimize away like as much mass, size, cost. We've got to trim all these things out and really trim the fat. And so as we approach the kind of physical limits, we really need to understand in much more detail, how much margin do I have left? How many more laminations can I take off the stepper motor before it's going to start to skip steps? These sorts of things kind of start to really matter, and we're kind of getting into that. So yeah, watch out for that blog post. There's some really interesting information, especially. Does anyone in here write firmware? Yeah, firmware writers around. Anyone write firmware? I said no. Basically, I think there's a lot of opportunity for more advanced control systems and controls algorithms in how we output filament. At the moment, we have things like linear advance. Effectively, what I'm proposing and hope to propose in this blog post is along the lines of a non-linear advance algorithm. So it should all be able to be done open loop without any more sensors and servos. I think that with a more intelligent model, we should be able to get more accurate extrusion with no additional hardware, just through software changes. So I'm quite excited for that, and also excited for the products that this is going to allow us to develop and how kind of close to the wire they will be in terms of their performance and size. Other things coming soon, so Titan Aero V2 Mini, which is kind of the product that we're talking about optimizing. Basically, it's the next generation integrated extruder hot end nozzle all in one package. I expect that we can carve at least 30 to 40% of the mass, size, weight, and really reduce cost as well. Rocky, which is something Rory's been developing, which is that nozzle with the flippy side to side. That's on the way. It's a great fun product. It's got a bunch of challenges in precision and flick over, and also we've just been spending a lot of time working on the tool changer, which in some ways obviates that. But we're still going to plow through and release Rocky, because it's a great product. It has a lot of applications on machines that already exist, instead of requiring everyone to buy a whole new machine designed from scratch. Nozzles, even smaller. I was surprised to see the people in the community have managed to push 0.15 millimeter nozzles to their limits, printing things like mini figurines and jewelry and stuff like that. And so we've got better machinery now, so we can make smaller nozzles more accurately. So there will be like 0.1 millimeter nozzles coming out. Very hard to use and make, but for some people, they have an application. We've got a new type of high temperature sensor, kind of like a PT100 or a thermocouple, that allow you to go to very high temperatures and be extremely accurate. However, what's cool about this one is it should be able to be plugged into a standard kind of thermistor output without any additional kind of amplifier hardware and stuff. So that's great. We have these things called Mordor beds. We've actually got them over on the stand. They are an extremely high power heated bed for printing at high temperatures. So easily achieving 200 degrees on the bed surface for printing your kind of Ultem, PEEK, PPSU, PSU type materials. And then we've got something called the Vari Power beds, which is something we've been doing for a long time. We did it first time around on the big box beds, where we modified the amount of power that we put in the beds across the surface area. Normal heated beds use a uniform amount of power across the whole bed. However, that leads to the corners being a bit cooler and the center being a bit hotter. We thermally image that and then change the amount of power density going into the bed, so it even things out. We are basically doing that again, better and for more beds and more sizes rather than just for only the big box. So those will be coming out soon. Onto the tool changer, which is what you're here for. As I've spoken about Midwest, it's not a printer, it's the basis of a printer. Pardon me, got a really bad heartburn today. The electronics, hot ends, and extruders need to be added. There's a reason for that. That's because we want to allow people to kind of configure and build their machine to suit their specific application. The pre-orders have been selling really, really well, so we're definitely going ahead. We're in the process of optimizing and going in the design for manufacture. It will still cost over £1,000, but hopefully not much more than over £1,000. And we've got a survey going on. You can find that on the blog post. Probably a few of you already filled that one out, so thank you. One of the big changes from what we first thought we were doing is that we're going to make this thing partially assembled. So it's still going to be flat packed. So it's kind of best of both worlds. So the construction of the machine is essentially you have a top plate, the extrusions to give it the Zedd height, and then a bottom plate. We are going to pre-assemble tram and tension and put on, so the entire XY motion system at the top, we're going to pre-assemble that, which means we can do it to a really high degree of precision, very accurately and very consistently, and it removes a lot of the fiddliness from you guys. So that'll be done. And then the Z-axis is the same deal's happening, so that'll be assembled extremely straight and tram. And then all the user has to do is come along to and basically sandwich the extrusions upright between the top and bottom plate, do up kind of 10 screws along the top, and then bolt the bed onto the front of the Z-axis. There's basically no, touch wood, margin for error in doing this. The planarity and orthogonality of the machine is defined by the fact that there's a piece of flat tooling plate at the top, which defines the XY plane, and then the levelness of that XY plane is defined by the length of the extrusions that have been cut, and you bolt all of that together. And so no matter how much kind of you try and misalign everything, as long as you do up the screws, and we've done our job in manufacturing things precisely, then the machine will be inherently orthogonal, flat, straight, trammed, and perfect. So kind of excited about that. It does mean that there's a little bit more time because we have to build the kind of production line and documentation and operating procedures for putting that all together. But I think it's a really nice enhancement for the machine for it to arrive, and basically it's, you know, a half an hour job to sandwich the whole thing together. Along with that, I should also point out that the guys at Duet have agreed to do a full wiring pack and board package. So that will just plug directly in and all the wires be of the correct length and ready to go, so, which is really nice. So it means that you'll be able to buy the motion system and an electronics system that plug together completely and is kind of leaves you ready to go. Just add hot ends and filament as you see fit. So I want to go into the details of this a bit. I don't want to bore you guys with stuff we already talked about in Midwest, but I think it's really important to point out the importance of that top plate being a single machined object from inherently flat tool plate. Everything bolts to that plate, and that plate defines pretty much everything about the position and flatness of the machine. So our high wind rails bolt onto that, all of the belt tensioning and idler posts bolt onto that. So everything is kind of defined off of that. We've got the carbon fiber gantry bar. It's a bit of a kind of, you know, it's a bit extravagant, but I really do think it's money well spent. It cuts a lot of mass off of that moving part and allows the accelerations to get up. And again, the high wind rails, can't stress enough how good those high wind rails are. We're using 12 millimeter high wind rails on Y, where it's stationary, and then the X-axis rail that goes across, that has to move, so to cut mass, it's down to the 9 millimeter rail. All the belts are planar. It's the core XY Fab Totem style. It basically doesn't have any of the racking problems of HBOT that you may have heard of. It's got a very tiny amount of torque that gets applied to the head, but it's really, really small, and the high wind rails resist it really well. We've found these belts from Gates. They're not the standard Gates belt. They're a type of belt that's, I think it's designed for clean room applications, where the belt is designed not to shed, like, you know, the black dust that comes off the belts and accumulates at the corners. In order to do that, they coat the face of the belt, i.e. where the teeth are, with a kind of non-woven nylon fabric that kind of gets, I don't really know how it's made, but it's kind of melted in there. What's really cool about that is it stiffens the teeth up a little bit, and it makes them run more smoothly over the pulleys. And so when you go round a corner, you change direction, the system has some flex in it. And so your actual true position of the head will overshoot slightly due to deflections in the machine. Some of that is electromagnetic deflection of the motor, gets twisted off of its kind of set point. And then some of that is true stretching of the belt, and that gets minimized by using good quality belt that has a lot of aramid in the back. But also one of the points of flexion is where the pulleys and the belt, those teeth interface, and those teeth, when the force is applied to them, the tooth deforms ever so slightly. And so adding on this nylon and enhancing the stiffness of that tooth actually has a notable effect on the ability of the machine to hold position under deflective forces. So yeah, they're a neat little find, and we'll also be selling them separately on the website soon. Cool. I also just want to point out, you can see the importance of this, that XY motion plate, and how everything is bolted to that with machine standoffs. Because all these parts are machined on precision, it's the same stuff we use to cut nozzles and heat breaks, so it's extremely precise. And it means that everything is extremely accurate and well defined in terms of its position. There really isn't the ability to assemble this machine and have axis skewed or things like that, especially with us pre-assembling the only parts where there is any ability to add, not play, but kind of misalignment. We'll be removing that kind of error source. So hopefully everyone should have a very, 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 very accurate machine. Zedd, we have changed, and we've changed it since I last spoke about it as well. So before, and on the machine you see out there, the Z-axis motor is bolted and is part of that top XY plate. In order to make the machine flat packable but pre-assemblable, we have had to decouple Zedd from the XY motion system. So now the Zedd motor sits at the bottom and points upwards. We have one big, fat, high-wind linear rail to which the cantilevered belt mounts. And so the whole Z-axis, rail, motor, lead screw, moving nut, and the kind of carriage that holds the cantilevered bed is one axis. And that gets bolted on just like the other pieces of extrusion. And then to the front of that, so this picture isn't actually representative of the new design, this is the old design, sorry. Onto the front of that, you then mount the bent piece of aluminium that holds up the bed. And so it's a really easy assembly process. It's just 4 screws that mount on the entire bed holding bracket. And it's very stiff. I think we Greg, you did the simulations on this. I think it's 4 kilos, which we theorize is like the maximum feasible amount, because you can only, there's 4 tool heads, load them up each with 1 kilogram of filament and print all 4 spools onto the bed, and put 4 kilos as far forward as you can. The worst possible deflection under that load is it's like 200 microns, something in that. Less? How much? What? 80 microns under the worst possible load conditions. It's also very harmonically stable. I don't know if you guys ever like walked past an Ultimaker or an Ultimaker 2 and seen it has that kind of like jitter, because although the bed is quite stiff to static deflection, it gets a bit of a kind of wibble going on, especially when the machine is moving. We don't have that really through sheer brute force of stiffness. Yeah, I'd just like to talk about ways we tried to do. Lots of people come and ask, like, oh, why didn't you do this? Or have you seen so-and-so's method for doing this? And yes, we have. We tried everything. And I want to talk a little bit about what we did and tried and what didn't work and why we chose the very specific approach that we did select. So magnets, electromagnets, electropermanent magnets, we tried all of these. So to start with the electropermanent magnet, which is something that Lulzbot were experimenting with for a while. We talked to them a lot. We bought some of the same electropermanent magnets. An electropermanent magnet is this weird hybrid between a permanent magnet and an electromagnet. You can basically, you fire a big pulse of energy into it, and it turns itself into a permanent magnet, so it doesn't require any ongoing current. So you can turn this magnet on, and you can then actually turn the magnet off by scrambling all the fields, and you can even reverse it. We didn't use those because it's really expensive. They're like 30, 40 bucks a pop. They're big, and they're heavy, and they're quite hard to package into the head. Then the reason why we didn't use electromagnets is they consume way too much energy, and they use a lot of current in order to generate the amount of force that they do have, and in doing so they produce a lot of heat. They're also not that small, and they're kind of hard to package around. And then again, the reason why we didn't use permanent magnets is that you have to, with a permanent magnet, you would have to have some other device or way of moving. So I've explained myself badly. In order to use a permanent magnet, you would have to move the head in and latch into something and then pull off in some other direction. And that kind of necessarily involves using up more space in the X direction, which means you can cram fewer tools onto the carriage. So we wanted to avoid that, so we didn't go with magnets. Another way that things are picked up in industry a lot of the time is vacuum. And vacuum I really liked. It was a really great solution in many ways. It's kind of like the Bowden system of pickup, because you don't have the actuator on the head. You kind of transmit the energy up a pipe and suck onto things. It works really well. But it does kind of have some issues. One is that you have this kind of loud, expensive pump kicking around. And the other is we were kind of fearful of debris or something else getting into that seal and breaking the seal. And when tool heads fall off, things go horribly wrong in the machine. It's really not great at all. So having a system whereby it's kind of inherently on or inherently off, even when there's no power or some kind of terrible incident occurs, if the tool head is positively locked on, that's a big benefit. And again, there are also a whole bunch of kind of really cool mechanisms for clicking things in and clicking things out. They just take up a bit more space, and space is really critical. And what it came down to is the fact that servo motors, and when I say servo motors, I mean the little radio-controlled servo motors, they've been tightly optimized for like decades now. And so you have this tiny little actuator that is, I don't even know how big those micro servos are. You have this tiny actuator that costs like a handful of dollars. It weighs like 10 grams. It can move an incredible amount of force with a surprisingly small current, and they're really easy to interface with. So they're kind of a bit of a no-brainer from there on out. If you think about the amount of performance that you get out of this tiny little servo motor for the price, it's really kind of unbeatable. So that's kind of our rationale for going with what we did. And the mechanism that we've built is if you turn off the power, and in fact we do turn off the power to the servo motor, the tool head stays latched on because it's positively locked into place with that bayonet coupling type fitting. So yeah, kinematic couplings are what we went for. If you've not heard of kinematic couplings before, they are a really fantastic way and a well-proven way of aligning things and positioning things. So they work on the principles of what we call exact constraint. You may have heard of over constraint or under constraint. Exact constraint is the happy medium between the two, where you precisely remove all 6 degrees of freedom with 1 point of contact, in summary. So you can see the 3 V-groove blocks there, and a ball sits inside of each V-groove block. By sitting in each V-groove block, you produce 2 points of contact. So we have, in total, around the 3 times 2, we get 6 points of contact in 6 different directions, each of them in turn removing 6 of the degrees of freedom. Provides an extremely precise pickup. We say 5 micron precision, even with the rough aluminium ones, but in truth, it's just because the dial gauges we have only go down to 5 microns. They seem to be more accurate than that. We bought an even fancier digital one, but really the imprecision is smaller than we are able to measure. So it really is just irrelevant. The amount of precision that you get out of a well-designed kinematic coupling it blew my mind. Really, really cool. The prototype parts that you see there are made of aluminium. They're kind of just handmade in the shop. In production, we'll be using hardened steel. Last longer, even more precise, if that's even possible. And yeah, we talked about servos and why we chose them. Light, cheap, optimized, proven. And you know, people in the printer world, we've been using servos for a long time for an assortment of applications here, in putting down bed leveling systems and so on and so forth. So lots of boards and electronics and firmwares already have the ability to control a servo built in. So it's a really useful way of interfacing with an actuator. Electronics, as I mentioned earlier, really happy to say that the Duet guys have done us a huge favor and taken away the wiring problem and all of the electronics, and they're going to be basically providing a full electronics kit, including wiring pack. That means that you can take your mechanical side of the motion system manufactured by E3D, couple it with the whole wiring electronics kit, and everything will just go together. It requires all of the electronics that you need to do everything, really. And the firmware and all of the documentation for that we will release and put on GitHub, of course. They've also, really got to hand it to the guys, they've made a couple of changes for us in the firmware, squashed a couple of bugs on our behalf, and generally done an amazing job. So we're kind of happy to call the Duet electronics and firmware our kind of go-to choice. Calibration. So if you see these little scales at the bottom, I don't know if you guys use vernier calipers before, where you have the little lines and you look for the ones that are the most well lined up. We're effectively printing vernier calipers on the bed. And then you go along and you look along so you print one in one head and one in the other. This is to get your XY offset. And you look for the most well-aligned 2 little notches, and you can see to within, I think, 25 or 50 microns how far offset you are. You plug that back into the firmware, and off you go. And then to figure out your Zedd offset, you peel off one of these and you measure it with calipers. So that's a great way of manually calibrating by eye. It takes a lot of the pain out of things, and if you're ever trying to calibrate a dual extrusion system, I thoroughly recommend that you give this a go for any kind of dual extrusion system. It doesn't need to be a tool changer. It works really, really, really well. One thing that we're going to try and do that we haven't implemented yet is use the kinematic coupling as a sensor in order to do tool offsetting measurement with the nozzle. So to explain this in more detail, your kinematic coupling is a bunch of contacts, and those are metal contacts. And if we turn those into a circuit, we can effectively, you can come along, and so if you have your nozzle and you go and impact it into the bed, you're going to deflect that joint. And you're going to deflect it, and if you deflect it enough, you will break one of those contacts. Especially if we put them all in series, then it only takes one contact to be removed, and you'll get an open circuit. That's all well and good, but actually breaking the circuit, i.e. applying enough force to the nozzle in order that the coupling actually loses contact, that's a bit troublesome, because obviously in terms of the mechanical design, you want to design the coupling to be as stiff as possible, and so you're kind of fighting yourself, because we're going to we're going to upgrade the kinematic coupling load carrying capability with bigger balls and larger contact surfaces, and stiffer springs to hold it all together. So it's going to require an incredible amount of force in order to uncontact one of those contact patches. However, what we can do, and this is well proven in industry, because it's actually how the majority of coordinate measurement machines, the big kind of aerospace measuring devices, worked for a very long time. What you do is you measure the resistance of that complete circuit. And what's happening is you have something called a Hertz contact, which is where we have a curved surface touching a flat surface. And when you get a curved surface or around like this spherical shape contacting this flat shape, you end up with a contact patch. We're applying a force, so you get some deformation, and so you end up with a circular patch of contact between those two surfaces. The size of that contact patch depends on the force being applied to those two objects. So as we vary the force, the size of the contact patch changes, and therefore the resistance changes. And by the time we tee up all of these resistances in series, and you have all these contact patches in series, you end up with an appreciably measurable resistance, and you observe that resistance for change. And so you can very easily sit there with a microcontroller and an ADC and observe and look for any change in resistance. This is really, really cool, because it allows us to do a couple of things. It lets us know for sure that we've got a head picked up for a start. It's yes, I've picked up a head, and it's in contact with all three. It's well located. It's not been knocked off. The next is it allows us to come along and use the nozzle itself for calibration. So we don't have any of this like separate sensor with the having to calibrate the amount of offset between the two. So we can come along, and yeah, you can level the bed as you normally do, but you're also getting the Zedd offset for your nozzle at the same time. And you can then subsequently get the Zedd offsets for all of your tools by coming along and touching. We can even further extend this, and we hope to, by putting some kind of post or ball in the corner of the bed, so probably replacing one of the screws for a pillar, and that will allow us to come along with the nozzle and touch the sides of that pillar in a couple of locations and get the XY offset as well. So if we manage to pull this off, it's going to be incredibly cool because it means that the tool changer then becomes basically a coordinate measurement machine that can measure itself and its own tools and potentially the objects within itself. So it's a big prize. It's not too difficult, I'm going to say, on account of there's a lot of prior art here, and it's been done before in terms with coordinate measurement machines. So big prize, some work to do, quite excited about it because it's going to allow the machine to completely self-auto-calibrate all of these tools. It's going to give the machine to know absolutely that a tool is engaged and locked and loaded, and also it means that if we come along with a nozzle or anything else and we turn the nozzle off, let it cool down, we could actually go back and measure the part by touching on the part, and just like a coordinate measurement machine does, and verifying that we've accurately printed what we thought we printed. And it will work not only with nozzles, but also with things like subtractive tool heads as well. So cutting bits and milling cutters and such like. We'll be able to calibrate all of that stuff and use everything. So yeah, it's really, really freaking, it's my kind of pet project, kind of next enhancement to do. And yeah, working with the Duet guys to do that will be really fun. Oh, I've got a laser pointer. No, I don't. Never mind. Yeah, we've not been doing as much work as we would have liked in terms of designing more special tools to go on the machine, because we've been focusing a lot on getting it built, designed for manufacture, and also the pre-assembly process, so it arrives assembled. But yeah, we do, the one on the far left is pretty neat. That's Rory's kind of side project. It's a, was it Raspberry Pi Zero? Yeah, and the new Raspberry Pi camera with a macro lens on the underside. And so it's basically a network connected camera that you can go and pick up. And the intent is that we can go and then pick up that camera, and then every layer you could go along and capture an image of the print, stitch those images together, and then turn those, you basically have a record of the entire print being created as it goes through the printing process. So you kind of capture all of that data. So it would be interesting for measurement and consistency, verification of prints, which is kind of difficult because in terms of non-destructive testing, it's very hard to look inside of a part. But if we're basically taking a photo every 100 microns through the part, it's basically you've got like an MRI CT of the entire part as it's being built, which is pretty neat. And then we have designs in the works for fitting all manner of E3D heads on there, including Volcano and so on and so forth. Future uses and other things to get in there. Greg Holloway, who designed the machine, actually used to design laser cutters before he came to us. So we want to get lasers on there. I'm not even really sure why or what I want to do with them or what we're going to have on them, but there's going to be some use, at least for part marking. And I'm not 100% convinced it will work, but there's a potential to do some amount of hybrid manufacturing, as in additive, subtractive, using lasers. And if we can do that, and if it does work, it would be very, very, very neat. So it's worth a go. But even if it doesn't work with lasers, we absolutely 100% want to do subtractive manufacturing. So we call it ASMBL, additive subtractive manufacturing by layer. So print one layer with an additive head, drop off the additive head, pick up the subtractive head, and go and trim that layer back down to size. So you intentionally overprint and then cut the part back. The advantage of doing this is obviously you get a huge improvement in surface finish and accuracy and so on and so forth. But if you do it in this particular way, print one layer, cut one layer, the amount of work that your cutter has to do is very low. So you can use a very small cutter, potentially even a drag knife, to go and trim the part. So it's a very, very promising, hugely exciting thing to do. really non-trivial in terms of the software requirements. Someone's going to need to write a slicer in order to do this. I think you probably have to be a madman to write a new slicer from scratch these days, but I reckon that it would be easy enough to write an add-on for Cura or similar that would go along and add subtractive toolpaths. Other things we'd quite like to do is try inkjet. Inkjet, again, useful for part marking, and I think that there is, well, obviously it's been proven by XYZ, who I think they have a patent on it for using an inkjet to color the part as it's being built, which will be fun. And another huge one, pick and place, and we're not talking about pick and place in terms of the traditional electronics pick and place where you're just picking up little resistors. We want to use kind of larger grippers, and have you guys have seen those grippers that are like a balloon full of sand and you suck the air out of them and they grip onto stuff? Something like that in order to pick up objects like bearings and captive nuts or threaded inserts, parts of this nature that we can drop, and even electronics, whole electronics like sub-assemblies like boards and the like, and drop them in. So we're effective. If you combine this with subtractive manufacturing and inkjet for coloration, you're kind of very rapidly trending towards the ability to, I want to say print, but it's more like automatically manufacture ready-to-use parts on demand. So we're not talking about components, but we're more talking about products now. So we can integrate electronics, other mechanical components. We can ensure that dimensions and surface finishes are greatly improved. And so it's a really exciting kind of platform for integrated manufacturing. Rather than just 3D printing, all on one platform. So very excited. It's a long road towards this, and I really don't want to downplay the kind of the difficulties and challenges ahead with doing all of these things. And any single one of these things is a big ask. And so there's, we're sitting here proposing these ideas to kind of seed those ideas within the community and hope that kind of experts will pick up from here. We're going to do our own bits. I think our next task is going to be subtractive manufacturing, because we know a thing or two about cutting things, so we've done that in the past. So we're going to give that one a go. But lasers and pick and place and inkjet, those are all low-hanging fruit that some expert out there, I imagine, will be able to take up. So very excited for that, and also the software is going to be a huge ordeal. The software for this is going to be a monster. We're going to have to integrate, CAD and CAM and slicers and form some sort of integrated package that is able to cope with and understand electronic schematics, GD&T data, color, surface texture, CAM and slicing all into one package. That is probably one of, if not the hardest task among all of these. Closing thoughts. The software is a huge deal. We really need a lot of work there. But the tool changer provides a platform that is, it's a reference design. And we're not trying to make the printer to end all printers, but we're kind of trying to show how something might be done. We're not getting into the game of building 3D printers, but we are in the game of assisting other manufacturers in making their printers better with well-made sub-assemblies and components. And so printer manufacturers out there that we're talking to, and these are big names. So for example, we're talking to Lulzbot, and they're very seriously working towards integrating tool changing into their machine. And so we want to enable as many manufacturers of 3D printers and independent makers to construct their own tool changing 3D printers and see what comes of that. I think that's everything from me. I've prattled on. I have no idea what the time is. But questions, thoughts, comments? Yes. The what? Oh, the rocker. Okay, yeah. So it's I can't quite hear. I'm sorry. It rotates about a pivot. It's basically it's two hot ends, but the two hot ends axes are not parallel, so they're offset like that. And you flick one from side to side. It's a Bowden-fed device, so the best way to describe it is kind of like I don't know if you've seen the E3D Chimera, but yeah, it's like a Chimera that's bent in the middle and then has a bearing and a shaft bolt that it rotates around, and then we use a little hobby aircraft servo again to actuate it. The servo isn't strictly necessary if you've got the ability to push on the device with the machine's axes. So you could put kind of hard stops at the ends and use that to push the thing from side to side. So yeah, Rory is again on that one. It's got some small challenges with that kind of locating and finding a right balance between the ability to be able to click it over and also for it to positively lock, and you've got to kind of balance those two whilst keeping everything very accurate, which is a little bit challenging, but I think it's most of the way there. It just hasn't been getting the tender, loving care that it needs to kind of push it over the line in terms of getting it ready for release, because we've been working so much on the tool changer. Yes. I would say not sooner than 4 weeks, but not longer than 8. Yeah. Ooh, Super Volcano is in manufacture now, so that should be in like less than 6 weeks on the way. Heater cartridges are also in manufacture, so that should all be kind of ready to rock in 6 weeks. Hi. It's Claire. Hi. Yeah, so all of it will be open source, completely under permissive licenses. And yes, we will also release the source for the tool changer, the mechanism, and we'll also be selling the parts of the tool changer, so that if you want to build a tool changing 3D printer that isn't our tool changing 3D printer, or you want to adapt it onto your machine, that's our objective number one, is to enable as many people to build tool-changing 3D printers of different types. We're trying to set a standard and prove that something can be done and make it not difficult for others to replicate. Because our evil money-grabbing plan here is if we can make everyone's printer require 4 hot ends rather than 1, then we're kind of in the money, right? That's the great evil master plan behind all of this. And also, I think that our current design is, it's what I would call it like forward locking. So it attaches and detaches from the side. But for Delta machines and the like, that's inappropriate and doesn't really make sense. So once all this is done, in terms of the tool changing machine that we're doing, I think we will look to build a system that is appropriate for deltas. So again, and deltas are inherently triangular anyway, and so they lend themselves really nicely. Or in fact, if anyone else wants to design it and use parts of our components, i.e. the balls, and cut the V blocks and the coupling mechanism, i.e. the socket and the bayonet fitting, give us an email if you want to design that. We'll help you out. But I think that's our kind of next task after that, is to allow this to be done from a top grabbing rather than a side grabbing mechanism. So just take the same technology, rearrange it, use the same parts as much as possible. Next. All out? All done? No? Cool. Thanks very much.